Hi everyone. Today we're going to talk about isotopes and mass spectrometry. You're going to need your notes, a calculator, and your periodic table. So we're going to learn how to read a mass spectra and what mass spectrometry actually is. And we're also going to calculate average atomic mass, which is a review topic from Regents Chem. Let's go over a few terms before we get started. Relative atomic mass is defined as the weighted average of all the mass of all the atoms in a normal isotope. Elements occur in nature as a number of different isotopes. Just a reminder that isotopes are atoms with the same number of protons and electrons, but they have a different number of neutrons. Because they have a different number of neutrons, their mass number is going to vary. And one last reminder, that just because the number of neutrons vary doesn't mean the properties of these atoms change. Since it is electrons in atoms that affect chemical properties of a substance, isotopes of the same elements are going to have the same chemical properties because they have the same number of electrons. Here's my first review question for you. Considering the following pairs, does either pair represent a pair of isotopes? And you should have picked B. Isotopes, again, are the same element, so they're going to have the same number of protons and electrons, but they have different mass numbers, so they vary by the number of neutrons. Up here, we have two completely different elements, and therefore they cannot be isotopes. Average atomic mass is a calculation that can be applied in order to calculate the mass that you see on the periodic table of elements. It takes into account all of the naturally occurring isotopes for an element. In the box, you can see that I gave you the equation. Again, average atomic mass is a weighted average, so it's going to take into account the percentage, or how often each isotopes occur, and the actual mass of each individual isotope. Remember that this sum of symbol right here means we're going to add together each of these for each isotope. And then we'll divide by 100 in order to get rid of the percentage. Relative abundance of an isotope is the percentage of atoms within a sample of an element that have a specific atomic mass. So basically, we're looking at how often does that isotope occur, and what is the mass of that specific isotope. All right, let's do a practice problem together. So we're going to calculate the average atomic mass for chlorine. I'm going to write our average atomic mass equation here. So chlorine has two isotopes that occur in nature, chlorine 35 and chlorine 37. These isotopes happen to exist naturally in the approximate abundance of 75% to 25%. Those numbers just happen to work out nicely. So let's solve our problem. So we're going to take the percent of each isotope. So 75% of chlorine 35, that 35 is our mass number for that isotope. And then we're going to do this for the next isotope. And we're going to add the sum of 25% times the mass, divide by 100 to get rid of the percents, or you could have written both these numbers as decimals. And when you plug this into your calculator, you should get 35.5 AMU, which is exactly what's on your periodic table, or very, very close to it. And here is the average atomic mass of chlorine, which once again, the reason we do this is because whenever we have a sample of chlorine, it is understood that it's actually a combination of chlorine 37 and chlorine 35, so we use this average atomic mass for our subsequent calculations. Now it's your turn to try. Neon has 3 isotopes, with the masses 22, 21, and 20 AMU. If the isotopes have the abundance 8.01%, 1.99%, and 90.00% respectively, what is the average atomic mass of neon atoms? All right, and you should have gotten average atomic mass equals, I'm going to take the mass times the percent abundance plus the mass times the percent abundance plus the mass times the percent abundance, all over 100. One thing I want to point out, 20 AMU has a 90% relative abundance. Your answer better be very close to 20. Make sure you're checking your work and that the calculation you do actually makes sense. These numbers kind of tell you where you got to go. So 21 isn't very abundant and 22 isn't very abundant. So when I plug this into my calculator, I got 20.2 AMU, which is very close to 20 AMU, which has the highest abundance. So always check your work. All right, on to the new topic, mass spectrometry. Mass spectrometry is used to detect isotopes and provide evidence for their existence. The machine used is called a mass spectrometer. It uses an ionizing beam of electrons in order to analyze a sample of the element. It ends up turning the atoms within the element into cations. This results in individual ions that are then sorted by mass, which we'll take a look at what that graph looks like in a second. A sample of the element will contain atoms of different number of neutrons, aka isotopes, so we'll be able to detect a number of distinct ions with different masses within our spectrum. This is useful because it allows us to identify different isotopes, figure out their relative abundance, and then with that information we can calculate the average atomic mass of an element. Here's what a mass spec looks like, right here on the right. So we have a pure zirconium mass spectra here. The things to make note of. So first is the number of peaks. Every peak is going to represent a different isotope that naturally occurs for that element. Make note of the height of each peak because it gives you the relative abundance to each of the isotopes. Y-axis gives you the percent abundance or relative abundance. And then the x-axis provides you, well, with a few different things. Sometimes it's the mass-charge ratio, so that could be the mass of the isotope to the charge of the ion. It can give you mass number, but more often than not, it gives you atomic mass, like we see here. Now let's look at a type of question. Based on this spectrum, what is the most common naturally occurring isotope of zirconium? Zirconium-90 is the most naturally occurring because it has the highest peak, followed by, it's hard to tell, zirconium-94, 92, then 91, then zirconium-96. Here's what a mass spectra typically looks like when it's printed straight from the mass spectrometer. So here you can see there's a mass to charge ratio on the bottom, percent abundance. There's 4 peaks for the chromium. And sometimes it'll even provide you the percent abundance. So right from this graph, we get the mass of each isotope, the percent abundance, which then allows us to calculate the average atomic mass of a sample. And here's our last problem for today. So rhenium is one of Earth's rarest elements. It's used in X-ray machines. The average atomic mass of naturally occurring rhenium is 186.21 AMU. There's 2 common isotopes. The masses are provided down below in the table. Use this information in order to calculate the percent abundance of each isotope for naturally occurring rhenium. Just a hint, you're going to have to use a system of equations in order to solve this. All right, so let's review this last question. So we have the average atomic mass of rhenium. We have the mass of isotope 1 and isotope 2. And I've written the average atomic mass equation here. So I'm going to start plugging into our equation and see what we're missing. So 186.21 AMU. Percentage is what we're looking for. So I'm going to put X for isotope 1. I'm going to put the mass for isotope 1. And just so I keep track of my variables, I'm actually going to write an X right in the table. We add this to our next isotope, which I'm going to call Y. I don't know the percent, that's what I'm looking for, but I do know the mass. So right now we have a 2-variable equation. Now, here's the thing. I know that all of the percent abundances have to add to 100. Instead of dealing with percents, I'm actually going to deal with the decimals, just so I don't have to worry about dividing by 100 right now. So I can take X plus Y equals 1, because I know that the decimals have to add up to 1. I'm going to solve for Y, so Y equals X minus, 1 minus X, there we go. I'm going to plug this back into my equation. So I got X times 184.95 plus 1 minus X times 186.96. Now I only have one variable to deal with. So what I would do next is I would actually distribute and combine like terms. And when I do so, I end up with negative 5.01x plus 186.96. I'm going to subtract 186.96 from both sides, and I end up with negative 5.01x equals negative 0.75. And when I divide both sides by negative 5.01, I end up with 0.15 for X. All right, so I have my percent abundance as a decimal for X, or isotope 1. I'm going to solve for Y again. And you get 0.85. Now if I want them as actual percents, I just multiply by 100. Isotope number 1, or X, has a 15% abundance. Isotope Y has an 85% abundance. All right, that's all I have for you today. We're going to practice with this a little bit more tomorrow in class. If you have any questions on the video, just ask me at the start of class, or feel free to shoot me an email. Otherwise, have a great day.